Okay, I'm going to go through some of the homework from last week so that you can look at that if you haven't tried it. Make sure you know how to do some of these different problems. So the first one is kind of similar to ones we did in class, where we've got a tricycle. So I've got a badly drawn tricycle here. It's got one big wheel in the front and two small ones in the back. If you had a tricycle, if you remember what they look like. And so we want to know which wheel has the greater linear speed and which one has the greater angular speed. Okay, so this is like the ones we did in class where we looked at the gears and the two cars that had the two different size wheels. So this is along the same lines as those. The tricycle's moving at the same displacement per time. It's got the same linear speed. So that's like delta x over delta t, or here, arc length over time. Okay. So that's going to be the same. V is going to be the same. So that means for the bigger wheel, which has a bigger radius, it's going to have a smaller angular velocity. And then the smaller wheels, which have a smaller radius, are going to have a bigger angular velocity. These are two combinations that each give me the same value. So we've looked at that again. We looked at a few examples of that in class. So the smaller wheel is going to have the greater angular velocity because it's got a smaller radius. Okay. Okay. Right now, we're all moving in this very moment at hundreds of miles per hour because the Earth is rotating. So, would people in Texas be moving faster or people in Alaska? And why? So, here's my terrible drawing of the Earth with Alaska and then Texas roughly. So, we see that Alaska is farther north, right, than Texas. If we think about this globe, think about the radius, okay? Texas is going to have a greater radius than Alaska because of their placements. In terms of their angular speed, we've got this relationship where if we're doing a full rotation, our angular speed value equals 2 pi over t. That's our radians traveled per time. That's the same 24 hours for everybody on the Earth, no matter where you are. So everybody's got the same angular velocity. So if this is the same, radius is different, then that means if you've got a larger radius, you're going to have a larger speed. Texas has got the larger radius because of its placement, so it's going to have a greater speed than if you're in Alaska, and that's linear speed. Everybody's got the same angular velocity. If we're thinking about a full day rotation. How long does it take the Earth to experience a rotational displacement of pi over 2 radians? So we actually talked the other day about pi over 2 being the same as 90 degrees. That's a quarter of a circle. We went through where you can solve that if you take your full circle, which is 2 pi radians over 360, and then you want to know how many degrees pi over 2 is. You can solve that. You get 90. A lot of people also knew this just from prior knowledge from math. Okay. So a quarter of the circle, if we travel the entire circle in one day, then that means this is a quarter of a day. And a day is 24 hours. So it takes about 6 hours, or 1/4 of 24, for the Earth to go through pi over 2 radians. Okay, for these items, indicate whether they're a frequency or a period. So this is just going back to period, which is time to complete a cycle, and then frequency, which is number of cycles per time. Those are an inverse of each other. So the second hand of a clock takes 60 seconds to travel around the clock. So it takes 60 seconds to travel once. That's a period. That's a time to complete one cycle. The hour hand of the clock travels around the clock 2 times every day, so that's number of times per number of cycles per time period, so that's a frequency. Earth rotates 30 times each month, that's number of cycles per time, so that's a frequency. And then Earth takes 365 days to complete one orbit, that's a period, that's time over number of cycles. Okay, and then we'll start looking at some of the kinematic equations. So here we've got a wheel. He has a radius of 5 meters. He starts from rest and is given an angular acceleration. So that's our change in angular velocity per time. And that's our symbol for that is alpha. Angular acceleration of 15 radians per second per second. And we want to answer a few questions for the time 0.5 seconds after the acceleration begins. So first question, what's the wheel's angular velocity? We can use this one of the kinematic equations because it's the simplest, and we've got this, and we've got this. So final angular velocity is initial, which is 0 because it starts from rest, plus my acceleration times my time, and I get 7.5 radians per second when I do that. Through what angle has the wheel turned? So that is a displacement. That's like saying how far did something go, okay, when we look back at linear kinematics when we had length. So we want displacement. So for that, we could use this equation. The one with time and displacement. We know our initial angular velocity again was 0 here because we started from rest. So that's going to give us 1/2 times alpha times t squared, 1/2 times 15 times 0.5 squared. And that gives me 0.5 times 15 times, 0.5 squared, 1.88 radians. So that's going to be in radians because that's my displacement. What is the speed of a point on the edge of the wheel? Okay, so this is a linear speed. So this is like a point here. What is the speed of that point? And that's where I can use the velocity equals radius times my angular velocity. And they give me my radius is 5 meters. And I figured out that my angular velocity was 7.5 in part A of this. So that gives me 37.5 meters per second. That's going to be in meters per second. Because this is meters. And then this is radians per second. The radians is, I don't know, it's kind of like, I guess, similar to cycles up here in these equations. We're not going to continue to include it. We're really like converting it into a meters per second measure, I guess. And then what's the magnitude of the total acceleration of a point on the edge of the wheel? So this is going to be our tangential acceleration, which we didn't really we've talked about it. We didn't get to cover a whole lot of it in class. Okay, so this wheel, let me draw another picture here so we can see better. This wheel has got multiple accelerations happening. It's got an angular acceleration because radians per second are changing per time. It's got a tangential acceleration because it's moving in a linear motion as well. Also, it's moving in circular motion, so it's got a centripetal acceleration. And so we didn't get to go through this in detail in class. I'm going to try and do it as part of starter type questions. But when you want total acceleration, you see that I've made a right triangle here. We're going to use the Pythagorean theorem. We're going to need AT squared plus AC squared equals total squared. And we'll, like I said, we'll try and go through that. But if I want total, or I want tangential acceleration, that's going to be r times alpha. That's another one of those little equations that links linear quantities and angular or rotational quantities. That's going to be 5 times 15 is what we had in this problem. So that's 75. And that's going to be meters per second per second. My centripetal acceleration is v squared over r, and that's back from circular motion. Let's see, v is 37.5. We got that in the last question. So I got to square that divided by 5. And that's going to give me, I'm kind of running out of room here, sorry. $281.25, is that right? Let me double check that. 37.5 squared. Yeah. One more time. 281.25. And then I'm going to use the Pythagorean theorem to get this total combined, because it's rotating, so it's moving in a circular motion. It's also moving with a linear motion. And so if we want the total of those two, and this is not including this angular acceleration, that's a different quantity, then we're going to use the Pythagorean theorem there, which is, a lot. But so we got 75 squared plus 281.25 squared equals my total squared. And I'm just going to work that out here. So I have 75 squared plus 281.25 squared gives me 84,726, blah, blah, blah. I need the square root of that to do my final step. So 84,726, as much as I can remember. So 291, and that's going to be in meters per second. That's a pretty big number. So, but that's my hypotenuse here. So, okay, so this video has gotten really long. Hopefully it will save. And I'll continue on the next one.